Hello everyone, myself Krishnaveni, working as assistant professor in Department of Physics from Marri Reddy Institute of Technology and Management. So as of now, I completed two modules. That is, one is Introduction to Quantum Physics, Black Body Radiation, Photoelectric Effect, and second module is about de Broglie hypothesis, matter waves and its properties. This is the module 3. In this, I am going to explain about the Heisenberg uncertainty principle. So let us go for the Heisenberg uncertainty principle. First, Heisenberg uncertainty principle was proposed in the year 1927. So the 1927 Heisenberg was proposed the uncertainty principle. So here there are the statements for the uncertainty principle. That is, general statement is it is impossible to know specify simultaneously and preciously any pair of variables that describe the total behavior of the atomic system. So if you take any atomic system, uh, that is any pair of variables, that is a pair means two variables cannot able to calculate simultaneously as well as absolutely, that is preciously and simultaneously we cannot able to find the any pair of variable that describe the total behavior of the atomic system. That is general statement. So here what is the meaning of this? That is, one variable we can find one time but not both at a time. That is the meaning of the statement. That is general statement. So statement number 2 here, it is impossible to know, particularly here statement number 2, it is impossible to know exact position as well as exact momentum of an object at simultaneously or same time. So we can find any one time we can find position, another time we can find momentum, but not both the same at a time. That is the statement number 2. It is generally any pair of variables, specifically it is position and momentum. That is statement number 2. Statement number 3, here it is impossible to know exact time as well as exact energy of an object at the same time, that is simultaneously. Means here any pair of variables, that is general statement, position and movement, it is particular statement specifically, and statement number 3, it is only exact position, exact time as well as energy. So here what is the meaning of this? One time we can find only one variable but not both. That is the meaning of this statement, that is Heisenberg uncertainty principle. So let us prove the statement. We are going to take two wave groups. Let us prove the statement number 2, that is we can find position and momentum of any object, that is at a time. That can be proved by using the by considering the two wave groups. One is narrower wave group, other one is wider wave group. So here basically what is the meaning of the wave group? So wave group here, it is a group of waves having the same amplitude, same intensity. The group of waves is produces a wave group. So wave group is since a group of waves having the same amplitude, same intensity, that group of waves is produces a wave group. So if it is a narrower, that is if the amplitude and intensity is less, then it is a narrower wave group. If the amplitude is more, then we can say that it is a wider wave group. If otherwise, simply we can say that if the particle is vibrating in a small region, then it exhibits the narrower wave group. If the particle is vibrating in a large area or large location, then it exhibits the wider wave group. So large means wider wave group, small area means it is known as narrower wave group. So why we are going to take the wave groups to prove the statements of the Heisenberg. So that is, first, before quantum mechanics we have the classical mechanics. So by using the classical mechanics, one can find the position and momentum at any instant of time. We can find position and momentum by using the classical mechanics. But after discovery, after development of quantum mechanics, there is impossible to find position and momentum at a time. That is by Heisenberg was found. That is known as Heisenberg uncertainty principle. So first we are going to take the narrower wave group. Suppose if the wave group is narrower, what is the meaning of narrower? That is, if the particle is vibrating in a small region, then it is a narrower wave group. So when the particle is vibrating in a small region, it exhibits a narrower wave group. When it is vibrating in a narrower wave group, we can find only the position of the particle but not momentum. Means if the particle is vibrating within the small region, that is, let us accuracy of finding the position of the particle within the small region, that is what we can, one can find only the position or location of the particle, that is more accuracy is finding the position of the particle, less accuracy is finding the momentum of the particle. So if the wave group is narrower, the probability of finding the position of the particle is more accurate, and when it is narrower, the momentum of the particle finding is less accurate. So this is a narrower, one time we can find here it is location but not momentum, that is when it is the narrower wave group. So at the same time, when the wave group is wider means, again you know, when the wave group is having the large amplitude intensity, then it is known as large, that is wider wave group. When it is having the wider wave group, we can find only the momentum but not the position. Why? Because here the wave is well defined, having the wavelength, that is the length of the wave, that is the two crest as two troughs is the wavelength, that is the lambda can be well defined. Here it is a wavelength is not well defined. So in this case we cannot able to find the momentum but not position, but position. But here, whereas here the wave group is wider, the wavelength is well defined. If the wavelength is well defined, we have the relation from the de Broglie hypothesis. What is that relation? Lambda equal to h by p. If the wavelength is well defined, the momentum is also well defined. Means what is the meaning of this? When the wave group is wider, the momentum can be find more accurate, but the position is not, position is less accurate. Here the particle is vibrating from this region to this region. The length of the length will be, our distance is very high, so we cannot able to locate the particle where it is. So that's why location of the particle finding is less accurate when the wave group is narrower, and momentum is more accurate when the wave group is wider. So simply we can find, what you can conclude this from this: when the wave group is narrower, we can find position. When the wave group is wider, we can find the momentum, but not both. We cannot able to find momentum here, that is P cannot able to find momentum, but we can find only position. When the wave group is wider, we can find only momentum but not position. So here position is represented by X and momentum is represented by P. So position is less accurate when the wave group is wider. Momentum is more accurate when the wave group is wider. So here momentum is more accurate and position is less accurate. But here it is a position is more accurate but momentum is less accurate. So here the principle is proved by using the two wave groups. One is narrower, another one is wider wave group. So here there is a uncertainty in finding the position is represented by delta x. There is uncertainty in finding the momentum is represented by delta p. So delta x is finding of the position uncertainty, finding of the momentum is uncertainty in momentum, that is delta p. So what is the statement proved by Eisenberg, that is delta x into delta p is very greater than h by 4 pi. That is statement number 1, having the principal mathematical expression, that is delta x into delta p greater than or equal to h by 4 pi. And if delta t and delta e are the uncertainty in time as well as here there is a time and energy. Here delta t is uncertainty in finding the time and delta E is uncertainty in finding the energy. So delta T is uncertainty in time, delta E is uncertainty in energy. So what is the statement of the Heisenberg uncertainty mathematical principle, that is delta T into delta E very greater than h by 4 pi. So here there is a small wave group, that is narrower, there is a larger, that is a wider wave group. So when it is a large wave group, we can find what? Momentum. Here when it is a narrower, we can find only the position. So here the delta x is small because it is a length will be very small, but delta p is very large. Why? Because lambda is small, lambda equal to h by p. If p is small, lambda is large. So next one here, delta x is large but delta p is small. Why? Because lambda is large. So del lambda equal to h by p. So if lambda is large, p is small. So the quantities of delta x, delta p, that is uncertainty in position, uncertainty momentum, narrower, small is having the quantity delta x, large is having the delta p. When it is a wider wave group, delta x is large because the particle is from here to here, the particle is vibrating. So obviously we can say that um, it is having the large, and delta p is small. Why it is small? Because lambda equal to h by p. If the lambda is large, delta p is small. So this is what Heisenberg uncertainty principle, general statement, specifically position and momentum, as well as time and energy. So by proving the statement, we have taken the two wave groups, narrower and wider. So when it is narrower, accuracy of finding the position is more and less accuracy is momentum, and when it is wider, accuracy of finding the momentum but not position. So next topic is in the quantum physics and solids, the next topic is Davison and Germer experiment. So Davison and Germer experiment is proved the matter has the dual nature or wave behavior of the matter by experimentally. So experimentally was proved by the Davison and Germer. By theoretically it is by de Broglie. So here the matter, wave nature of matter, that is wave nature of matter means again you have what you know, that is electron, proton and a neutron. This electron, proton, neutron, out of this electron, the fast moving electron are behaves like a waves. So here that was proved by the Davison and Germer. These both scientists was proved the fast moving electrons are having the wave behavior. And also what is the application of this, we can find the, we can use it to study the crystal structure, that is it may be a simple cubic, FCC, that is face centered cubic, as well as body centered cubic. So different crystal structures are there. So we can study the structure of the crystal by using this Davison-Germer experiment, that is that accelerated electron beam can also be used to study the diffraction studies of the crystal. So here what is the Davison-Germer experiment principle? We can find fast moving electron act like a wave, as well as that is application. What is that application? We can find the crystal study, that is by using the diffraction results from the electron beam. So this is the principle of Davison-Germer experiment. What is a Davison-Germer experiment? That is experimental verification of the matter waves was proved by the Davison and Germer, and theoretically it was proved by the de Broglie hypothesis or de Broglie. De Broglie is theoretical statement and experimentally it is by Davison and Germer. So next one, construction. So what are the components are required for the construction? So there are construction, in this construction there are the many components are required to prove the wave behavior of the matter. So what are the components are required? That is filament F, plate P, filament F, plate P, the filament is made up of tungsten material, plate P, nickel crystal, circular scale, collector and connected to galvanometer. So what are the components are required for the Davison and Germer experiment? That is filament F, plate P and nickel crystal Ni, and collector is C, galvanometer is G, circular scale. So these are the components are required for the Davison and Germer experiment. So components are required for the Davison-Germer experiment. The filament. So what is the use of the filament? The filament is used to emerge the electrons. It is emerges the electron. When it emerges the electron by applying a potential. What is that potential? Steady potential, that is constant potential is applied for the filament F. The filament is made up of tungsten material. The filament is made up of tungsten material and it has applied to 54 volts. Then what it releases, the filament is get heated, then it is emerges the electron. And then what is the use of the plate P? So plate P provides the uniform or collimated beam. So it is only single directional electron will be emerges from the plate P. And nickel crystal. So nickel crystal is used to study the diffraction study of the crystal. So the nickel crystal is only used. Why? Because the interatomic distance A interplanar distance. D, so this interatomic distance is the distance between two atoms is known as interatomic distance. Interplanar distance is known as the distance between the two planes of atoms is known as interplanar distance. The interatomic distance and interplanar distance having the same distance comparatively the wavelength of the electron. Though this, because of this reason, the nickel crystal is suitable to study the diffraction result. And next one is circular scale. So circular scale is used to measure the scattered beam of electron around the nickel crystal. And galvanometer used to measure the scattered electrons coming from the nickel crystal. And circular scale is used to measure the scattered beam of electron around the nickel crystal. And collector is used to collect the electrons from the nickel crystal. So these are the different operators are used in the Davison-Germer experiment. So here Davison-Germer experiment, in this we have the filament F. So we are applying 54 volt potential at a filament F, which is made up of tungsten material. When we apply 54 voltage potential, the filament is get heated, then it is emerges the electron. These electron will fall normally on the nickel crystal. So when it is fall on the nickel crystal, the surface rows of atom are act like a diffraction, the atoms of the or planes of the diffraction grating. So this single line of atom is known as single diffraction lines. So each and every plane is act like a lines of the diffraction grating. So this nickel crystal is act like a diffraction grating when the electrons is incident normally on the nickel crystal. When this wavelength as well as this wavelength of the electrons as well as interatomic interplanar distance matches, then it will shows the diffraction result. The diffraction result will collected, the scattered electron will be collected from the nickel crystal, that is collector. The collector will collect the all scattered electrons from the nickel. This is incident beam of electron and these are the scattered beam of electron. The scattered beam of electrons are collected by the collector. So here the collector is maintaining a stopping potential or retarding potential. There are two names for this. One is stopping potential or retarding potential. So what is the meaning of retarding potential? Here the electrons which are coming from the filament is known as primary electrons. The electrons which are coming from the filament is known as primary electrons. The electrons which are generated at the nickel crystal is known as secondary electrons. So the collector is allowed only the collector is allowed only the primary electron. The collector is not allowed the secondary electron. Why? Because at collector it maintains the retarding potential or stopping potential. The stopping potential will stop the electrons from the nickel crystal but allows the electron from the filament. When the collector collects the electron, the galvanometer shows the deflection. So when it is shows the deflection, then there is a scattered electrons entering in the collector. So what is the name of collector? Another name of the collector is known as Faraday cylinder. Faraday cylinder. So this is about your construction part. Next one, working. So how it will be statement will be proved, how the principle will be proved, how the matter having the dual nature. Now we will see in the working part. So here the Faraday cylinder is capable to move around the circular scale, and for given accelerating voltage, what is a given accelerating voltage? 54 volts is applied. The electron beam is incident normal on the surface of the crystal. The nickel crystal is act like a diffraction grating. So at 50-degree angle, so what is the angle here between incident beam and scattered beam? There is a 50-degree angle. There is a 50-degree angle. There is a high intensity of the scattered electron. At 50-degree angle only, the rows act like a rulings of diffraction grating, and it will produce as the first order spectrum. The first order spectrum, this is spectral spot, and this is the first order, and this is the second order. Here we are going to considering only the first order spectrum. Why it is considering only first order spectrum? When it is going away, the intensity of the spots will go on decreases. That's why we are considering only the first order spectrum. So at 54 volts applied at the fifth filament, and the angle between incident and scattered angle will be 50 degree, then you will get the first order spectrum. So this is the diagram for the working. So here the scattering angle between the incident and scattering, there is an angle. That angle is taken on x-axis, and scattered beam of electron is taken on y-axis. When the angle is increases, at particular angle only the intensity of scattered electron will becomes to maximum. What is that angle? 50 degree angle. When we apply, what is the voltage we are applying? 54 volts. So the number of electrons on the collector is shows the maximum when the angle is becomes to 50 degree. So let us consider only 50 degrees but not all the values. Why? Because 10, 20, 30, why we are going to not considering? Because at 50 degree only we are getting the maximum intensity. That's why we are considering only 50 degree but not all. So here these are the structure of the nickel crystal. These black color spheres are known as atoms of the nickel, and these are all planes of the nickel crystal. This is the one atomic plane, and similarly there are many atomic planes are there. So how many atomic planes are there? 4 atomic planes are there. So here suppose incident beam coming from the filament is allowed to incident on the nickel surface, then it will get scattered. That angle is known as 50 degree angle. So here it is a totally 180 degrees. So totally it is a 180 degrees. So here out of this we have covered the 50 degree. So totally it is 50 degrees over. So here remaining 65 again with 65. So the 65 is make an angle with the crystal structure. So by substituting all these values in the equation, what is that equation? So here the Bragg's law is what? 2d sin theta is equal to n lambda. So we are applying the Bragg's law because a crystal is act like a diffraction grating. We are getting the diffraction results from the electron beam incident on the nickel crystal. So that's why we are going to take the Bragg's law, that is 2d sin theta is equal to n lambda, where t is what? Interplanar distance. What is interplanar distance? That is d. D is interplanar distance or interplanar spacing. So the value of this constant, that is 0.9 into 10 to the power of minus 10 meters. So 2d, d is 0.9 into the power of minus 10 into sine of 90 minus 25. Otherwise you can take 90 minus 25 r, which is making an angle with crystal, that is sine 65, which is making an angle with crystal, that is sine 65. Sine 65 is equal to order of diffraction is 1, lambda which we are going to find. So order of diffraction is 1, theta is the angle of scattering. So by substituting all these values, you will get lambda is equal to 1.648 angstrom. So according to de Broglie, this is what? This is what? Theoretical assumption. So this is what? Experimental. Sorry, this is experimental value. And here this is a theoretical value. What is a theoretical value? That is, what is a de Broglie? De Broglie is known as theoretical assumption. What is a de Broglie theoretical assumption? What is a formula? 12.26 by root V angstrom. So 12.26 by root V, what is the value of V? That potential is applied how much? 54 volts. Substituting these values 54 volts, what you will get? 1.668. So this is theoretical value and this is the experimental value. So difference between theoretical as well as experimental, that is 1.668 minus 1.648. So what is the value? You will get 0.02. So 0.02, it is in angstrom. Angstrom means 10 to the power of minus 8 or minus 10 meters. So what is the value? 0.10 zeros and then 2 meters. So you will get what? The difference between theoretical as well as experimental is very, very less. So what you can conclude? The de Broglie hypothesis is correct by using the Davison-Germer experiment. Davison-Germer experiment confirms the de Broglie concept of matter wave. So we can say that matter has the dual nature. One is particle nature and wave nature. That is by theoretically de Broglie and by experimentally was verified by Davison and Germer experiment. So principle, construction. Construction, we are using what are the components and what are the purpose of the components, and the in working how it will be working, what is the angle we are going to take, what is the potential we are applying, and result. In the result here there is a theoretical result as well as experimental result. Theoretical result is from Bragg's law Theoretical result is from de Broglie, experimental result from the Bragg's law. So these two values are coincide with each other. So Davis and Germer experiment confirms the de Broglie matter waves. So thank you. We will see in the next class. And here I have referred from the books called as Applied Physics by P.K. Palaniswamy.